All right, so we are going to talk about inverse functions today. So the first thing is, what the heck is an inverse function? Well, I am glad you asked. All right, so what an inverse function is, you guys probably have heard the word inverse in math, and inverses undo each other. That's really what it is. You know what the inverse function for addition is. It's subtraction, because subtraction undoes addition. What's the inverse function of multiplication? It's division, because division undoes multiplication. And by the way, multiplication undoes division. They're inverses of each other. One isn't the inverse and one isn't the original. They're inverses of each other. But what does this mean in general if we're going to undo? So let's think about, your function machine. And I don't know if you've ever seen like the idea of the function machine, but you definitely know about the idea of the function machine. So the idea of the function machine is we have this input, we put it into the function machine, it does something to it, and we get the output. Typically, we say you put x into the function machine, and your output is the f of x. Your input are the x values, your output are the y values. You put x into something, and you get the value of y out. You put something that's from the domain into the function machine, and your output is something from the range. So that's the idea of the function machine. And then what the idea of the inverse is we can go backwards. What? You can start with the output and put it into the function machine and come back to the input. And if you think about it, we're used to the idea of input being the x values and the output being the y values. But if an inverse is going to undo what the function machine is, our y values become the new input and our x values become the new output, because now we're going this direction. Well, if we're going that direction, it's like the x and the y values have switched roles. So, as far as how to find inverse functions, and actually I'm going to just generalize and say how to find inverses, and I'm going to talk about that why in a little bit, but how to find inverses. So I'm not specifying the word function, because inverses may not always be functions. But how to find inverses, if the outputs become the new inputs and the inputs become the new outputs, it's like our x and y values have switched roles, and that's exactly what you do. You switch x and y. And honestly, once you switch x and y, you have the inverse. Now, typically, we go ahead and still solve for y because we want to write it in as a function of y in terms of x. But once you switch x and y, you have your inverse. So let's look at what I'm talking about. Let's look at a simple example. So for example, let's say that we have y equals 2x minus 7, and we want to find the inverse. Well, we have it right here. To find inverses, you switch x and y. And so that's exactly what we're going to do. Now, remember, whatever you write on the next line mathematically should be equivalent to what you write above. And if it isn't, you should specify y. So, like, for instance, here, I'm going to switch x and y. I'm going to say x equals 2y minus 7. Now, this is no longer equivalent to this. So because I need to say, because it's no longer equivalent, I should specify why this is no longer equivalent. And it's no longer equivalent because now I found the inverse. So honestly, all you have to do is just write the word inverse in front of this, and then you're okay. And I've got the inverse. Now let's go ahead and still solve for y. So I'm going to add 7 onto both sides and then divide by 2. And I'll just go ahead and reverse the order. So the y is first. And so now I have the inverse written as a function of y in terms of x. But really, this is the inverse right here. And this makes sense, because let's think about what this says. This says, start with x, you multiply by 2, and then subtract 7. And this says, add 7 and then divide by 2. It's doing these steps backwards. So again, if we start with x, you multiply by 2, then subtract 7. If we want to undo that, we have to add 7 and then divide by 2. So it works. It makes sense that this is the inverse. And there we go. Now, a little note about notation. As far as notation goes, let's say I started with f of x equals 2x minus 7. So I actually used my function notation. Then the notation for the inverse of f of x, it looks like this. And then I'll go ahead and write that part there. Now, it looks like f to the negative 1 power of x, but don't ever read it that way. That's just really awkward. That's not what this is. This is the inverse of f of x. So the way you read it, it's the inverse of f of x. So now we can say that, if I have a function that's 2x minus 7, its inverse is x plus 7 divided by 2. And it's kind of nice to be able to do that. Like if we name the function f, then we know the inverse of f is going to be this notation. And it's literally the inverse of f. It looks like f to the negative 1 power, but just don't ever read it that way. That's going to make you look like you don't really know what you're talking about. But of course you guys do know what you're talking about because you're all math rock stars. But honestly, that's it. That's how you find an inverse. So let's see here. Let me look at my list. What else did I want to do with you guys? Let's do another finding the inverse. Let's do one that's not quite so obvious. I mean, like I said, you can just literally reverse the order of everything you're doing here. Multiply by 2 and then subtract 7. So undo it. You add 7 and then divide by 2. Let's look at another one. It's still the same idea. It's just not so obvious looking at it what the inverse is going to be. So this one will be, let's start with f of x equals 2x minus 1 over 3x plus 5. And we want to find the inverse of f of x. Now this time I don't have a y. And so if I don't have a y, how can I switch x and y? So we know that f of x is like our y, but we don't actually have the y in the original problem. So the first thing I should do is say let y equal f of x, so I can rewrite it with the y. Now remember, at this point, I haven't actually found the inverse. But now I'm going to switch x and y. And so now I have found the inverse. I mean, literally, I'm actually done finding the inverse. Now, the only thing is when it says to write your answer like this implies you have to take the inverse and solve for y, because you can't find the inverse function of f until you actually solve this for y. So we've done the first step, but now we have to solve this for y. Okay, now this one becomes a little trickier, because how are we going to solve for y if the y is in two places? Well, you have to do a little trick. So one thing in general, whenever you're dealing with something, you're like, I don't know what to do, but you have a fraction. A little trick is multiply both sides by the denominator. So I'm going to have this And then let's see what we can do with it. So I've just multiplied both sides by 3y plus 5. If I multiply x by 3y plus 5, I have x times 3y plus 5. But if I multiply this fraction by its denominator, it's going to cancel out, and I'm just left with the numerator. Okay, so now let's see what happens here. Now, how does this help? Because I still have a y in more than one place. How am I supposed to solve for y when it's in two places? Well, let's try to collect the y's together. But until we can do that, we have to free this y. It's trapped inside the parentheses, so I'm going to go ahead and distribute. And then what I can do is, and I don't know why I keep writing the 3 as a 2. That should be a 3. I am going to go ahead and collect all the terms with a y on one side and all the terms without the y on the other side. And just because I like to avoid negatives, I'm going to move this one over and this over here. That's going to minimize my negatives. All right, so I get this. Now I'm about to hit the bottom of my page. So normally we should always work down the page, but I will go ahead and make a second column. But here's what helps. By going ahead and collecting all my terms with a y on one side, I can factor out the y. And it will look like this. And now I have the y in one place. So now it's very easy to get the y by itself. I'm just going to divide both sides by 2 minus 3x. So y is 5x plus 1 over 2 minus 3x. And then the only thing I should do, since the problem says to find the inverse of f of x, I just have to write it in that notation. And there we go. So now I know that if I want to undo this, I need to use this. And it's a little harder to see intuitively because here I've got an x in two places, so I'm doing two things at once with the x. And how does this undo this? But it really does. If you were to take an x value and put it here and get an output, if you put that output in here, you would get the original value for x. And it would work. So that's how you find inverses. So the general gist for finding inverses is switch x and y, but usually we also solve for y. Now, how do you find inverses algebraically? Finding inverses algebraically. Well, let's think about this. Okay, finding inverses algebraically. I mean, we know to find them I don't want algebraically, I want graphically. We know from algebraically, you switch x and y. So if we're going to find them graphically, you still switch x and y. Now there's going to be another way to do it too, but I'm going to go ahead and put this here. You can switch the x coordinate with the y coordinates. Now let's take a look at what happens here. So I'm going to go ahead, let's try to draw this neater. I'm just going to set up some axes. We're going to count by 1 in each axis. Let's see if we can find a pattern of what happens when we switch x and y. So for instance, let's look at this point right here. This is going to be point A, and the coordinates of this point are 4, 2. Now if I switch x and y, because we know to find inverses, you switch x and y. So if I switch x and y, then I'm here at A prime, which is 4, 2, which is 2, 4. Let's try that again. So I've just switched the x and the y coordinate. 4, 2 went to 2, 4. Okay, it's hard to see anything yet. Let's try another set of points. Let's try this one right here. I'm going to call this point B, which is at 1, negative 2. So if I switch the x and the y coordinates, I go to negative 2, 1, and I'm right up here at B prime. And just so we can start seeing things, I'm going to go ahead and get rid of the actual coordinates. But all I'm going to go ahead and do is switch the x and the y coordinates. All right, so I got that. All right, let's try a few more points. Let's say I do this point right here, C, and C is at 0, 2, so C prime is at 2, 0. Again, I'm just switching the x and the y coordinates. Okay, let's try another one. Let's try this point right here. I'm going to call that point D, which is at negative 5, 2. So if I go to 2, negative 5, I'm down here at D prime. Do you see anything happening at all? Take a look at this graph and just see what you see. I'm going to go ahead, I'll plot 2 more points, and let's see if we can see what's happening. I'll go ahead and plot this point right here, point E. Point E is at 1, 2, 3, 4, 3. So it's at 4, 3. That means E prime is going to be at 3, 4. It's going to be right here. And for my last one, let's go ahead and do this point, which is going to be G. And G is at negative 3, negative 2. So G prime is at negative 2, negative 3. Hopefully you see some symmetry in this picture. And there's beautiful symmetry to this picture. This line right here, if we were to reflect this picture along that line, all the corresponding points would line up with each other. E would fall on E prime, A would fall on A prime, C on C prime, B on B prime, D on D prime, G on G prime. They're all a reflection about this, and this, you should know, is the line y equals x. So to find inverses graphically, it just kind of depends on what's more convenient for you. One thing you can do is switch the x and the y coordinates, but another thing you can also do is inverses are reflections about the line y equals x, which is kind of handy. And it turns out whenever you reflect about the line y equals x, you switch the x and the y coordinates. So it works out perfectly for that. And like I said, to find inverses graphically, you can think of it either way. It's just whatever happens to be more convenient at the time. To find inverses graphically, you can switch the x and the y coordinates, or you can think of it as a reflection in the line y equals x. It's the same exact thing. When you reflect about y equals x, you switch the x and the y coordinates. If you switch the x and the y coordinates, you're reflecting in the line y equals x. So these are equivalent statements right here. They have the same end result. So, for instance, let me go ahead, and I'm going to go ahead and do an example here. For example, let's find the inverse of y equals x squared. And we can do it algebraically or we could do it graphically. So let's try it both ways. Let's try it algebraically, let's try it graphically. So algebraically. So we start with y equals x squared, and we know the inverse. We switch x and y. X equals y squared. And there we go. We've got it. Now, it's going to be tempting to solve for y. And so if we do, we solve for y, we take the square root of both sides, and it may be tempting to want to say this. Take the square root of both sides. The square root of x, actually, you know what? Hang on one second. Just to preserve things, preserve all the steps, I'm going to show taking the square root on a separate step. And then we have this. So I switched x and y. That's my first step. Then I took the square root of both sides to get the y by itself. And of course, the square root of x is the square root of x, and the square root of y squared is y. Or is it? Think about that. Is that right? And hopefully you're remembering that that is not right. Remember, when you do an even root of a variable, you have to think of the absolute value. And then in this case, the absolute value does matter, so we're going to have plus or minus root x equals y. And just because it makes more sense to put the y first, I'm just going to reverse the order. So there we go. That's actually what the inverse of y equals x squared is algebraically. Let's look at it graphically. Let's see what this looks like graphically. We'll kind of compare the two methods here. So graphically, now hopefully you remember y equals x squared. That is a parabola, and remember it's a parabola that goes through 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. And it's this parabola right here. Now, we can think of it either way. We have some actual coordinates of points here. So to find the inverse, we could actually reverse the coordinates. Here, if I go ahead and put some points so we can have what we're referring to. So if A is at negative 2, 4, then A prime is at 4, negative 2. And if B is at negative 1, 1, then B prime is at 1, negative 1. And if C is at 0, 0, then C prime is, oh, well, it's also at 0, 0. And if D is at 1, 1, when you switch x and y, oh, well, you still get 1, 1. And then E is at 2, 4, so you switch E and you get 4, 2. So I have these 5 points. It ends up being this. But that also happens to be a reflection about the line y equals x. So again, it just depends on what's, and different people are different. Like if you can see what the reflection of this looks like about this line, you can go ahead and draw it. Remember, we want to be precise though, so make sure you get those points precise. So that's where also finding the coordinates and then just switching the x and the y coordinates can help. But there it is. And then this makes sense. Let's go back to finding the inverse algebraically. Remember when we took the square root? How that gave us the absolute value, which then gave us the plus or minus? Remember that if we just had positive root x would just be the top half. But because we have the negative root x also, that gives us the bottom half, which is good because now we have the full reflection of the pink in the blue. And so there we go. That's how you find the inverse, algebraically or graphically. To find the inverse algebraically or graphically, you can think about just switching x and y. But graphically, you can also think of it as the reflection in the line y equals x. Now there's another idea here, and that is of inverse functions. So now I'm going to go back to, what I was talking about in the beginning, how I wasn't going to use the word function at first. Inverse functions. Look at this graph right here. Is the inverse a function? And hopefully you're saying no. And we can see clearly that this blue parabola is not a function because it fails the vertical line test. And sometimes we do want functions. Now we could see from the original pink parabola that the blue parabola was not going to be a function, even if we didn't graph the blue parabola. Let's go ahead and take a look at this. So inverses as functions. Okay, so we know, let's look at y equals x squared. I'm going to go ahead and just quickly draw that right here. We know it goes through these 5 points. Now, we know we can look at this and see that the inverse will not be a function. And the way we can see this is not going to be a function. If I go back to this graph up here, remember the blue one failed because it doesn't pass the vertical line test? Well, remember switching x and y, the pink one fails the horizontal line test. And that's actually a test for an inverse function. So this parabola passes the vertical line test, and so that means the parabola is a function, but the parabola fails the horizontal line test. And that means its inverse is not a function. And so we don't even have to draw the inverse to know that the inverse of this won't be a function. We already knew that the inverse of the parabola was going to be something that would not be a function, because the original parabola fails the horizontal line test. And you may be going, what's the big deal about functions? And honestly, it just kind of depends on the situation that you're actually using these things in. But remember what the definition of a function means. It means for every input, there's exactly one output. I'm going to go back up here to this graph. So if we look at the pink one, if I put this value in for x, I know I'm going to get that value out for y. I don't have any other options. If I put this in for x, I get that value out for y. If I put this value in for x, I get that value out for y. But if I go to the blue one, let's say I put this value in for x. I don't know what my output is. I could go up here and I could have that output, or I could go down here and get that output. So I don't know. I could have this one. I could have this one. I don't know which one is the right one. And so there's some uncertainty there. We don't know which is the value that we want. And like I said, it kind of just depends on the situation you're dealing with. Sometimes we like to know where we're going. Given an input, we want to know what the output is. We don't want to have a choice. And so sometimes we want to restrict our inverse to a certain part of the graph so that we know it's going to be a function. And so that's this idea of restricting the domain. So let's say that we want to, actually let me change colors here. Let's say we want to restrict the domain of the function so its inverse is also a function. And let's just take a look at that original one. Let's look at y equals x squared. Y equals x squared. So this function that we keep looking at. So again, I'm going to just quickly redraw this. So let's say we have that. Now, right now, we know that this graph is going to fail the horizontal line test. That means its inverse is not a function. But we want to make it so it is a function, so we're going to have to restrict the domain. We basically want to look at only part of this graph, but enough so that it passes the horizontal line test. So which part are we going to look at? And honestly, you could look at just this part of the graph. You could look at just the left-hand side, and that would pass the vertical line test. However, that involves the negative numbers of x, the negative inputs. Typically, we try to stay away from that, so we can. If we just pick the positive values of x, then that stays away from the negatives, and it makes an inverse function. So if we say y equals x squared, but only look when x is greater than or equal to 0, that is restricting the domain. If we restrict the domain to x is greater than or equal to 0, the function passes the horizontal line test. So its inverse is a function. And sure enough, if we tried to do the inverse, if we tried to take the reflection of that, let's just pick these points and switch x and y. So starting with 0, 0, switch x and y, you're at 0, 0. Take 1, 1, switch 1, 1, you get 1, 1. Take the point 2, 4, you switch 2, 4, you get 4, 2. And sure enough, that blue graph is, it will be a function. It'll pass the vertical line test. So if you ever see a problem that says restrict the domain so the inverse is a function, take a look at the graph and take only the part of the graph you need so that it passes the horizontal line test. All right, let's take a look at one more thing, and that is this idea of, actually, I'm not going to make an example yet. Verifying inverses. To verify or prove functions are inverses of each other, let's take a look. What do you have to do? Well, remember that if we go back to the very beginning, we can take the input, put it into a function machine and get an output, and then we can put that output back in and get the input back. We can just do it backwards. So we're going to take an input and make it the output, and the output and make it an input. Wait, what? It's actually the idea of composition of functions. So if I take G and put it into F, that should be the same thing as taking F and putting it into G, and should be able to get the same thing each time. Can you think of what these both should equal? So let's think about this. Over here it says I start with X and I put it into G. So I start with X. X is my input and I get an output. I take that output and put it into F. I should be right back where I started with at X. Same thing over here. If I take the input of X and put it into F, and then I take that output and put it into G, it should undo it and get me back to where I started with at X. And that is how you prove or verify that functions are inverses of each other. And you always need to do that. You always need to, like if the problem says to verify or prove that you have inverses, you must do it this way. I'll show you what I mean and why I'm making a big deal out of that. Let's just take an example. And we're going to do two that we already know. We're going to do two examples here, and that'll be the end of the notes. So let's look at this first one that we did. Remember when we did 2x minus 7, and then we got x plus 7 over 2? We know that those are inverses of each other. So let's try it. So we're going to verify that f of x equals 2x minus 7 and g of x is x plus 7 over 2 are inverses. Now don't think that you can just go ahead and start with one, switch x and y, solve for y, and show that you get the other. That's not how you do this. You have to go ahead and do compositions. So that is exactly what we're going to do. We are going to show that f of g of x is equal to g of f of x, and that they equal x. This is one of the few times it's going to be okay to put one equation with two equal signs in it. All right, let's actually do it. Now remember how your inverse functions work, your compositions work. So f of g means we're going to take g and put it into f. So we're going to have 2 x plus 7 over 2 minus 7. And then here we're going to put f into g. So we're going to take 2x minus 7 and put it into x. So we're going to have 2x minus 7 plus 7 over 2. And we're going to show that you get x. And then this one's pretty straightforward. The 2's are going to cancel out on the left-hand side. So we're going to have x plus 7 minus 7. Over here in the middle part, the minus 7 plus 7 cancels out, so you have 2x over 2. And then, sure enough, the x is left. Over here, the 2's cancel out, so the x is left. X equals x equals x. So therefore, f of x and g of x are inverses of each other. So notice to verify, I didn't switch x and y. To verify, I had to use compositions and show that no matter which way you compose them, you get x. Okay, so here's going to be the last example. All right, here you go. Now this is the same example that we did above. We had started with this and we switched x and y and solved for y and got this. So we know that they should be inverses of each other, but now we're going to verify it. So verify that using the compositions of each other. And so remember, we need to show that f of g of x equals g of f of x, and that equals x. So this is a good one to practice your algebraic skills. Go ahead and pause the video right now, try it out, see how you do. Can you get this to work? All right, so I've gone ahead and worked it out, so let's see how we do it. So remember, the first thing is you have to do the compositions. You're going to have to put g into f. So here is g that replaced these two x's. That's where this came from. And then we have to put f into g. So here's f that went in place of these two x's. And that's where this came from. And we have to show that these two things equal x. Oh God, that seems really awful, doesn't it? But it's not so bad if you remember what we did with complex fractions. Because that's really what we have. We have a fraction within a fraction. So look for your common denominator. And these are really nice because in this first complex fraction, both the denominators are the same. So that's our LCD. So if you multiply by the giant 1, multiply top and bottom by that LCD, we can see what happens. And then the same thing with the second complex fraction. These two denominators are the same. So that's your LCD. So again, multiply top and bottom of the big fraction by that LCD. Now, if you had trouble with this and didn't know what to do, I would actually encourage you to take a look at this and see if you can finish it up on your own. So pause the video and try it out. But I will show you what it looks like from here. All right, so the next thing is, let me actually move this out of the way here. So remember, this denominator has to distribute to both terms in the top and the bottom. When it multiplies by the first term, the denominator cancels out, so you just have 2 times 5x plus 1 left. And then when it multiplies to this term, nothing cancels out, so you have minus 1 times the LCD. And then the same thing, this is going to multiply to both terms. When it multiplies to the first term, the denominators cancel out. And then when you multiply to the second term, nothing cancels out, so you have this. And then it's going to be much more straightforward after that. So the same thing happens here. This LCD is going to distribute to both terms. And so we have the same kind of result happening. This will cancel out with this denominator, so you have this left. And then it gets multiplied by 1. And then on the bottom, it's going to get multiplied by 2. But then it will cancel out with this denominator, and so you have this left. And after that, it's all really straightforward, because then we just distribute and combine like terms. So I distributed, I got this. I distributed here, I got this. When I combine my like terms, now things start happening. The 2's cancel out, and 10x plus 3x is 13x. Down on the bottom, the 15x's cancel out, 3 plus 10 is 13, and sure enough, that's going to be x. We have some stuff similar here. The 5's cancel out, and the 6x's cancel out. So we're left with 13x over 13, and sure enough, x equals x equals x. And by the way, to finish this proof, don't stop here thinking, oh yeah, and then you can see that it's going to work. No. You have to get it down to x equals x equals x. If this is a written problem on our celebration of knowledge and you don't write it down to here, you stop here and assume that your work is done, or even stop here and assume your work is done, it's not, and you're not going to get full credit. In fact, not only do you have to do this, but then when you're doing a proof, think of it as your concluding statement. Okay, so I've shown what I need to, So my conclusion, I know that f and g are inverses of each other. And by the way, if you've never seen this little triangle of dots, this is a mathematical symbol for the word therefore. So therefore, we know that f and g are inverses of each other. This is all required for your proof. Do not think this is optional. I am not just putting this in for our notes. You must put this in your final thing to get full credit for the proof. But that's it. That's the idea. If you ever have the directions that say verify that two functions are inverses of each other, you have to do the composition both ways and show that you get x. And you have to work it out all the way down to the bottom until you get x equals x equals x, and then state your final thing. And that's it. So there you go. Inverses in a nutshell. And I will see you in class. Bye.